Hello, I welcome you all to your own channel MSK Learnium. Now in this video we will solve one problem related to the heat transfer by using finite element methods. Actually the problem is from fin, that as you know the fin is an extended portion which is used to increase the heat transfer rate, right? So now we have a problem on the screen that for the fin shown in figure, determine the temperature distributions with two elements. Take thermal conductivity is 50 watt per meter degree centigrade and the diameter is 0.01 meter. So the figure is shown here. One element is there whose length is 2 meter. At this one end the temperature is 50 degree centigrade, that is the temperature of inner surface you can see, and the body where it is kept in a surrounding, that surrounding temperature or air temperature is 800 degree centigrade is given, right? The heat transfer coefficient of that surrounding air is 200 watt per meter square degree centigrade is given, as well as the heat flux value, which is Q is equal to 50 watt per meter square, is also given, right? So now the problem is mentioned, in the problem it is mentioned that we have to use the two element methods. Means what? We need to discretize this element into two parts. So the total length is 2 meter, so each part is 1 meter length. First of all, what we need to find means we need to get the stiffness matrix for element 1 and a stiffness matrix for element 2. That as you know that here is this problem is related to the fin, so fin formula we will use for finding the stiffness matrix. So first of all we will write on the given data, right? So here we'll go that this is our solution, okay, and here we have a given data, right? So given data means what? That you have a T1 is given, which is 150 degree centigrade. Surrounding temperature or air temperature is T infinite is given 800 degree centigrade. Thermal conductivity of the material is given how much? 50 watt per meter degree centigrade. 50 watt per meter degree centigrade. The heat transfer coefficient H is given 200 watt per meter square degree centigrade, right? As well as the diameter of that element is given, which is 0.01 meter, right? So the total length is given, L is equal to 2 meter, and heat flux, that Q is equal to 50 watt per meter square is given, right? We need to find out the temperature distribution, means when we discretize this body into two element, right? So here you have a T1, T2 and T3, node 1, node 2, node 3. So first of all we will find out the stiffness matrix. So here we go, that first we will write discretizing the given body into two element, right? So here you can mention that discretizing the given body into two element, right? Into two element, right? So now we will find out the stiffness matrix. So one element is like this, of having length is 1 meter, right? And these are exposed to the surrounding air. So here that from all surface is supposed to be convection, right? So here you have a T1 and this is the T2 and this is the infinite temperature, which is 800 degree. Infinite temperature means surrounding temperature, T infinity, and this T1 is equal to 150 degree centigrade. First of all what we need to do, that the length, as we have discretized the 2 meter length into two part, so this one length, one element 1 is having length is 1 meter, right? Now we can find out the stiffness matrix for that body, right? So here we can say stiffness matrix. So as you know the stiffness matrix for conduction is K is equal to AK by L 1 minus 1 minus 1. So but here it is the convection as well as the fin problems, right? So the stiffness matrix in this case, that K1 is equal to AK by L, right? It is 1 minus 1 minus 1 1, right? Plus HPL by 6 2112. This additional formula we have used. Why? Because it is the for FEM problems, right? So whenever the FEM is associated, you need to use the stiffness matrix for this way, right? So now first of all we will calculate the perimeter and area of the element. So perimeter is equal to what? That P is the perimeter. So P perimeter is equal to P is equal to pi into D. So pi into 0.01. So your answer will be 0.0314 meter. Alright, then we'll find out the area. That is, area of the element is circular. So pi by 4 into d square, which is nothing but the pi by 4 into 0.01 whole square, right? So this is what? 7.853 into 10 to the power of minus 5 meter square, right? So this given data we calculated. Now we've calculated A. You have a K is given, right? L you know 1 meter, H you know 200, P we calculated, L1 we'll substitute and get that values. First K1 will calculate. So here we go again. That let's find out the K. See this. So here, so here you can say that is K1, right? So K1 is equal to what? A is 7.853 into 10 to the power of minus 5. K is equal to 50, right? And L is equal to 1, right? Into 1 minus 1 minus 1 1. Alright, plus H is equal to what? H is equal to 200. Perimeter we calculated 0.0314. HPL into 1 by 6, right? Here only, that's continuation. This is you have a 2 1 1 2, right? So while you simplify, you will get the values like this. That is K1 is equal to, this is how on simplification you will get 10 to the power of minus 3, right? Into 3.92 minus 3.92 minus 3.92 and plus 3.92, right? And this term you have a plus 2.04 this is the 2.08, right? And this is 1.04, this is the 1.04 and this is the 2.08, right? So now you can add this. So K1 will get that 2:2 matrix. K1 is equal to 2.0439, 1.036, 1.036 and 2.083, right? So this is your T1 and T2, T1 and T2. As you can see in the problem that the element, when we discretize this, all values will be same. So it means that stiffness matrix 1 and stiffness matrix 2 would be equal. So you can say here that since K1 is equal to K2 is equal to what? Is equal to this, that is 2.0439, 1.036 and 1.036, 2.083, right? So this is what you have at T1, T2, and this element 2 is connected between T2 and T3, and this is the T2 and T3, right? Now we need to globalize them, so we can find out the global stiffness matrix, right? So global stiffness matrix means K is equal to K1 plus K2. So you have a 3 nodes in the problem, right? As you can see that here T1, T2, T3. So matrix will be 3:3 matrix will come. So you have a equation is like this, that is K is equal to, this is what we'll get, 2.0439, right? And this is 1.0360 and 1.036, this is 4.1269, 1.036, 0, 1.036 and 2.083, right? So this is T1, T2 and T3, T1, T2 and T3. This is column and these are the rows, right? Now we need to import the finite element equation. So you can say finite element equation, right? Finite element equation. So finite element equation is what? K T is equal to F. So K we already calculated. T means T1, T2, T3, nodal temperature. F load vector we have to calculate, right? So first we'll calculate the load vector for fin problem, right? So load vector for heat transfer fin, right? So load vector is equal to what? That F is equal to Q A L plus H P T infinite L by 2 1 1. In some problem the heat flux is not given, so this term will be 0, only you have to use this one. But in this problem the heat flux is given, so we can simplify these all values. So here heat flux is given 50, area you have calculated 7.853 into 10 to the power of minus 5, length is 1, plus heat transfer coefficient is 200 and perimeter we calculated, that is 0.0314 into 2. T is equal to 800 into 1 by 2 and 1 1, right? So this is what we got. On simplification you can see that load vector on simplification we have, this is here will go, that is, sorry, here we can say that F is equal to 2512, right, and 2512, right? So this is what 2512. All right, now so as we don't have any force at 1, right? So this is what you have a 1 2. So now you can say K T is equal to F, right? So K is equal to what? That same matrix we can write here now, right? So this is what you have a 2.0439, 1.036, 0, 1.036, right, 4.1269, 1.036, 0, 1.036, 2.083, right? And this is what we have a T1, T2, T3 is equal to this is F1, that is F1 we have a 0, right? And F2 is equal to what? 2512 and 2512, right? But we need to modify this equation. Why? Because at node 1 temperature is known, that is 150, right? So this, at this load vector we will add this temperature, whatever the temperature we know at the node 1, and for these F2 and F3 we can modify, means multiply the second row second column value with the node temperature and add this with load vector, right? So first we can say that this equation will be modified again like this: 2.0439, 1.036, this is 0, 1.036, 4.1269, 1.036, 0, 1.036, 2.083, right? And T1, T2, T3. As T1 we know, so here in place of F1 we will substitute the node temperature, right? That is known temperature, and this is 2512 and 2512. Further we have to modify this equation, means these load vector should be modified. So now what you need to do, that second row and first column value is multiplied with known temperature, right? With known temperature, temperature and add with load, right? So that is what you can say 1.036. this is the second row, first column, right? This value is multiplied with the known temperature which is 150 and add with the 2512. So the answer is 2667, right? 2667.4. so now the equation will become like this. That is, again we can write down this equation here: 2.0439, 1.036, this will be 0, 1.036, 4.1269, 1.036, 0, 1.036, 2.083, right? And the temperature is T1, T2 and T3. This equation is become like this, that is 150, right? And these load are modified by this value, that is 2667.4 and 2667.4, right? Now as the first temperature at node 1 is known, so the first row, first column would be eliminated, right? So by elimination approach, this first row and first column is eliminated. The matrix is reduced into 2:2 form, right? So on elimination, that equation will become 4.1269, 1.036, 1.036 and 2.083 into T2, T3 is equal to this load 2667.4, 2667.4. Two equation will get, that is 4.1269 T2 plus 1.036 T3, this row is multiplied with this column, is equal to 2667.4. Next equation we have 1.036, this row is multiplied with this column, T2 plus 2.083 T3 is equal to 2667.4. So when you simplify these two values, you will get that T2 is equal to 371, right? That is 371.28 degree centigrade, and T3 is equal to 1095 degree centigrade. So this is how we can solve the problem which is related to the heat transfer problem, specifically that for FEM, right, by using the finite element methods. Thank you.